This project has been slowly developed and improved on over the course of 6 months, and even though it does cut metal, I want to let you know that you will be watching this machine change a lot. So in other words, take what you see here with a grain of salt. There are many ways of doing something, and this is just how I built my machine the way I saw fit at the time. Also, this video is focused on the computer-controlled frame that you will see me build, not on the plasma cutter itself, which I bought for $300, which is actually pretty cheap for a plasma cutter, and I highly recommend this Amico one I have since it put up with all my shenanigans. Anyway, enjoy the video. Alright, so I understand it may not be intuitive as to how a X and Y coordinate system can work with pulleys. So I'm just going to try to explain that with a piece of wood. Now all we want to do is have this stick slide up and down like so. But if we connect the stick to the string like so, then as you can see, there's a problem. So now what we have is a second independently working loop of string. So now what we do, we connect both of these loops of string together on one side, and that allows both of the loops of string to move together. Now both sides of the string are moving in the same direction, which means the stick will move in the same direction at either end. What we have effectively done here is we have made a fully functioning axis. So this is a fully functioning y-axis. Alright, now we can do the same exact setup for the x-axis. Now if we add two freely moving straws around the sticks and connect both of these straws together with some tape, you can see that now we have a pointer on this X and Y coordinate system. And we can move this pointer diagonally and pretty much in any kind of direction that we want. So this is basically how my machine moves, but this is also how an Etch-a-Sketch moves on the inside as well. So hopefully you found this demonstration useful to understand my machine a little bit better. This is a very simple and cost-effective way at making a coordinate system, and honestly, I really love how this is designed. So I did go to Ace Hardware and I did get the bolts and nuts necessary to complete this project, and this hardware that you see in front of you is a little less than $5 worth of parts, which is actually really nice. That's pretty cheap. Now these bolts and nuts are both imperial. The threads on them are imperial, and I did look at the metric equivalent of these bolts, but the metric equivalent is $2.50 or somewhere around there, and I wasn't about to pay over $2 for one bolt. So yeah, I went with imperial threading and it was much cheaper. Each bolt was 75 cents. So yeah, I would have went with metric, but I just don't want to spend over $2 on one bolt. For those that are curious, this is a 5/16 of an inch bolt, and the metric equivalent is an M8 bolt. Now I bought the bolts to fit through these roller skating wheels because I was going to turn these wheels into pulleys, which I don't recommend doing. It's really not worth your time. I used a file to create this trench in the rubber wheel, and I did this manually for most of them until I realized that I wasn't getting even cuts. Now, I didn't expect even cuts really, but I thought it honestly wouldn't matter that much once the whole system was under tension. Yet it does matter. So I had to create this jig with a Dremel, and after that all my cuts in the wheels were even. And just talking about this now is just ridiculous. I wish I didn't go through all that effort just to make pulleys out of these wheels. Next up were the corner posts, and here are the dimensions for that. I started with cutting sheet metal that I had into the shape that I needed. Then it was a lot of filing, more cutting, bending the metal, and more bending. I was becoming an expert metal bender. I marked the center here, and center punched it to drill it out. The bolt fit through nicely, and I just had to screw on the nylon nut. Repeat that 3 more times, and you will have 4 identical corner posts. Now I need to install these on the frame, but let's pause here and talk a little bit about the wooden frame. It's nothing special. It's made from common 2x4s, and I made the frame as big as the steel tubing I had. My 2 biggest limitations were the length of the steel tubing and the length of the 2x4s I had, which were both approximately 47 inches long. Because of the way I constructed the frame, I had to mark out different points on the corner posts so when I screwed on the corner posts, it wouldn't interfere with the screws that were already there holding the frame together. I then started putting on the pulleys with 2 nuts separating the pulleys apart, so I had the option of adjusting the height as necessary. Now you're going to see me use braided steel wire for this, and unless you have strong metal pulleys or are dealing with a huge identical machine with a lot of tension, I do not recommend going with steel wire, as you will quickly find out it cuts up the rubber pulleys, and it's generally difficult to work with and required me to heat treat it in order to get most of the curly shape out of it. Alright, so we have both of our loops done, and they both work pretty flawlessly. I'm liking how this looks. So I'm using these cylinders with a screw on the inside to basically secure the existing loops we already have on here. Now, however, I have one over here on, I guess you could call this the x-axis, and I have another one right here, and this is probably going to be the y-axis. And what I'm thinking of doing is just wrapping a loop around the wheels and making all the loops on one axis connect over to this little guy so we can secure all of them on this one piece of metal. Alright, so I stopped doing this halfway through. I just want to show you how this is being connected. So the additional loop, the second loop we're putting on, has been strung through this metal piece, right? And I'm putting it over the roller. And this is the second loop, right? And I have to put it underneath this roller and then have it come back up all the way back to this guy, and I have to put it through this guy and tension it. And the way I'm going to tension it is simply pull it down. Once the wire is through and once the wire is secured onto the bench vise, all I have to do is just pull this down manually and then screw it in, and then it'll be tensioned. Both loops will be tensioned and also connected together. So hopefully that makes sense. There's probably multiple ways of doing this, but this is the way I'm doing it. All right, so I tensioned everything together, and it was looking okay. It was working, right? But then I noticed that it started to really twist up and get tangled, and when it started getting tangled, this basically started to happen, and yeah, we do not want that. So I did heat treat all of the wires so they're fairly straight, but that still doesn't stop the twisting. And as you can see, I put this piece of metal in between the 2 wires here, and the same thing on the bottom, and you can see past that point it looks fairly good, and then just where this piece connects all the wires together, it just looks horribly twisted. If I try to move this, right, what I notice is that the twisting keeps getting worse and worse, and then these pieces of metal keep spreading further and further apart. And well, I'm just going to have to figure out a way to fix this. And if I can't fix it the way it is now, then I'm going to have to add another pulley, basically redesign the wheel a little bit to make sure that the two loops of wire are separated and not in the same crevice or same channel. Okay, so this is kind of funny, but I was so worried about this problem, but it ended up being such a simple fix. I fixed the problem with 2 sticks and some tape. Look at this. It works so well. It works so well, and it's so simple. This is, wow. It's crazy. I mean, now we can move on, but like nothing gets tangled anymore. Alright, so I fast forwarded a little bit, but I didn't do anything too complicated, so I'll quickly bring you up to speed. So to control these motors, to control this whole system, we're going to be using the parallel port of a motherboard. Now, I chose this computer. I had a few different computers I could have chosen for this job, but this computer had a nice form factor and it's not really bulky, so I like this computer to control the motors. Now, in order to access that parallel port right here that we want to use with this computer, well, we're going to have to install Linux CNC on it. Now, Linux CNC is available for free as a free download, and what I like to usually do is just download the ISO file, the image file of Linux CNC, put it on a flash drive, make that flash drive bootable, and then just plug it into this computer where I can then install it. Now, there's a very handy program called Rufus, and with Rufus, I just simply select the USB that I want to use in order to, install the system, and then I tell Rufus to use the image file of the Linux CNC and just basically put that on the USB, and that's how I installed the system on this computer. So nothing really complicated there. Alright, so once you have the system up and running, you go to the top left and click on the application menu. You go down to CNC, and there you click on Linux CNC. Once you're over here, well, ignore for a second my configurations. There will be a sample configuration drop-down menu, and you go to By Interface. You have to click this By Interface drop-down menu, and then you have to find the Parallel Port tab. Once you find that, go down to Stepper. This is what I'm currently using and experimenting with. Now, there's a couple of options here. You can do a simulation in inches, you can control the steppers in inches, and you can control the steppers in millimeters. So I just chose to control the steppers in millimeters. I selected that option. I also selected Create Desktop Shortcut, and then I clicked OK. And then I just clicked yes and OK and OK, and there you go. It makes a shortcut and then immediately opens the application. Now, in reality, you're not ready to control anything yet, so you have to exit out of this, and you have to go to Home up here, then go to Linux CNC, and then go to Configs. Now, these two are the same, but the one we just made is this one. Alright, so once you get into the folder, you'll see a lot of different files. Now, really, there's only 2 files that will concern you. So all of these files go directly from the standard pinout HAL file. You can change this. There's a different pinout HAL file, but really I don't want to confuse you right now because there are a lot of options to change stuff around. But really, this is how I'm doing it. So really, the only 2 files that should concern you is the standard pinout HAL file that's right here. And basically in this file, it shows you all of the physical connections, all of the connections that concern you regarding the parallel port. So basically what I'm saying is if you want to know what wires to connect where on the parallel port, then you have to look inside this file. It will show you basically. Now say you wanted to change values, parameters, you wanted to change numbers regarding, I don't know, error values, acceleration values, brake values, whatever it may be. You would go into your .ini file. Now, in my case, in my configuration, that file is the stepper underscore millimeter .ini file. It may be different for you if you choose like the stepper underscore inch.ini file. So keep that in mind. You have to go into the file that concerns your specific configuration. Now, once we go in here, you can see that there are a lot of options. Now, if you look over here, you'll be able to see all of the HAL files that this specific configuration will use. The standard pinout HAL file is just fine, and I think it's the default in this specific case, but if you wanted to inverse your direction and step pins, you could do that by trying to use a different HAL configuration file. So that option is available to you. You just have to make sure to get rid of that pound icon in the beginning of this line, and then the system will use this configuration, this new configuration that you told it to use. Alright, so hopefully you can see there are numbers here at the end of the parallel port, and to find the correct pins that I want to use in the parallel port, I simply hook up my multimeter to one of these pins that I'm looking for, and then on the other end of the cable, I just tap with my multimeter each wire to see if there's a short circuit. And so what I'm doing is a continuity test. That's how I find the correct pins to use, and that's how I've been doing it forever. So yeah. So for the motor controller, I'm using these easy drivers. Now there's three things you have to keep in mind when working with these. You have to first of all make sure that you are inputting the right signals to drive the motor. So basically what you need is the step signal, the direction signal, and a ground signal for the signal return path, basically. Now the step and direction pins will be displayed in the HAL file that I just went over. Next, you have to power this motor controller. So I use these two pins, this is ground and power. Now for the power, I use a 12 volt 2 amp laptop power supply, and that seems to work fine. I think you can go up to 36 volts if I remember correctly, but you're going to have to read that yourself. I'm not exactly sure the limits of this motor controller, but 12 volts at 2 amps is just fine for this purpose. Now you can control this motor controller with 5 volt signals, or you can control this controller with 3.3 volt signals. Now I haven't had any trouble with controlling this board at 3.3 volts from the parallel port. Now the final thing is to just keep in mind how to connect the stepper motor over to this board. You connect the stepper motor wires to these connections. So there's an A side and then there's a B side, and these sides come in pairs. So one quick little side note, because this sometimes trips me up, is that I'm connecting the cable ground. So this shielding wire and all of this shielding stuff is the cable ground. I connect that over to the signal ground of this board, and that ground pin is right next to the step and direction pins. So keep that in mind. This is an important connection to make sure that your step and direction signals have a return path and that the motor is not twitchy. Now, like I mentioned, on the controller board itself, there is a pair of A wires and a pair of B wires that we have to find on the motor in order to properly connect these wires to the controller board. Now, in order to find the right configuration or right pair of wires, we have to use this multimeter and set it to its continuity setting. Now, all we have to do to check which pair is which is connect one lead of the multimeter to any of the 4 wires and then just check the rest. And there you go. So now we know that our yellow and blue wire are a pair. And that also means that our red and white wire is also a pair. So we found our two pairs of wires that we have to connect over to the board.
Now, I don't want to talk about the motors because I ended up replacing them anyway. All the salvaged motors I used were simply too weak and got way too hot during operation, and that's why buying a stepper motor is the way to go in this case. I went from a braided wire pulley system, where I had to learn how to splice steel wire, to a printer belt pulley system where I learned how to connect fiberglass reinforced belts with fishing line, to finally a proper timing belt pulley system that I'm using now. However, you will see that I had to make an adjustable frame for these stepper motors out of some scrap sheet metal I had, and that frame luckily fit the new stepper motors I eventually had to buy. If anybody is interested in the exact dimensions of this frame, let me know in the comments and I'll take some measurements.
Alright, so I just got these bearings today, and these are 16mm linear slide bearings. Now, I've been looking at them, and they work fantastic. So this rod that I'm using, or these types of rods, because I have a few of these, so I don't know which ones I'm going to use yet, but all of them are 16mm in diameter, and so far these bearings fit perfectly on these rods, so everything's fine there. But there is a problem with these bearings. As you can see, these bearings are not square, they're rectangular. And you can tell if I turn one on its side that the holes don't exactly line up, they don't match. And this creates a problem because what I want to do, I need to position these bearings in opposite directions, and I need to place one on top of the other. And I basically need to mount both of these bearings together like this. Now the four holes that are present on these bearings are drilled and tapped. They're drilled all the way through, you see that clean hole, but they're only tapped halfway through. So I was originally thinking of drilling and tapping my own holes into these blocks, but I think the best option in this case would be to simply, instead of mounting it like this, like I wanted to, I'm going to mount it like that. And no, I'm not going to try to put anything in between these holes. What I'm going to do instead is make a metal bracket all around this entire block. So I cut out this piece of metal, and this is going to be the bracket for the bearings. And as you can see, I have made lines where I need to bend this piece of metal, but the problem is that this doesn't fit too well in my bench vise, so I have to figure out another way to bend this. Alright, well, I managed to finish the bracket, and yeah, it works pretty nicely.
Here is a close-up of the whole assembly. You can see how I connected the linear bearings together, and also how I connected the plasma cutter head. I drilled some holes at the end of the tubing that will serve as connection points for the wires or belts. I used a self-tapping screw here, and that worked just fine.
Now there's one big software issue that we have to overcome, and that is turning the plasma cutter on and off when necessary via the G-code. And obviously you need to connect a G-code command to a parallel port pin. And there's a couple of ways we can do that in Linux CNC, but I did it in the most simplest manner that I could find. And so starting from your desktop, you go to Home, Linux CNC, Configurations, then you go to your configuration folder, and then you go into your standard pinout HAL file. Now once you're in this HAL file, you'll be able to see that I added these two lines of code. And basically all this is doing is connecting the digital out pin to a parallel port pin. Now, digital out is one of the options that they give you when you're configuring all your pins in Linux CNC. And I remember noticing this, but I never knew what digital out was for. And apparently it's for just general things like toggling your coolant on and off, or toggling your spindle on and off in a CNC machine. However, in this case, we're just using it to toggle the plasma cutter on and off, because Linux CNC was never really designed for plasma cutting operations. However, now there's much more support for it. Now, this machine does not use a Z-axis. Maybe I'll add one in the future with an auto leveling system, but for now we're just using the X and Y axis with this digital output that we are routing over to the plasma cutter so we can turn it on and off. And that's strictly the bare essentials, bare minimum that we need to make this plasma cutter work. The Z-axis will be fixed for now. So once you're done connecting your digital output to your parallel port pin in the HAL file, in this case I'm using pin 8 in the parallel port, well, you can actually control pin 8 with G-code M64 and G-code M65. Now, a quick little note, you can add more digital outputs. You can actually add more than 3, because 3 digital outputs are already supported built into Linux CNC, but if you want more digital outputs, more than 3, then you can add more. You just have to configure some different files. I'm not sure if it's exactly in the HAL file. I didn't read up on that specific process, but I know it's possible. So if you want more digital outputs, that's definitely possible too. So this is the setup I have so far, and as you know, in the software we connected digital output 1 to pin 8 on the parallel port. Now what I did, I found pin 8 on the parallel port. I connected pin 8 to my circuit, which basically consists of a resistor, in-channel MOSFET, a diode, and a 5-volt relay. Really, that's all it is. That's all it consists of. And with that circuit, I'm able to control anything, even this light bulb. However, we're not controlling a light bulb. Just imagine that this light bulb represents the plasma cutter for now. Now, fundamentally, how this is going to work is when we send a G-code file to Linux CNC to execute, that G-code file will contain obviously our specific G-code that would control pin 8 on the parallel port. Now, pin 8, of course, is connected to the circuit, which in turn is connected over to the plasma cutter, which this light bulb represents. But for now, all I want to do is demonstrate this system, and so I'm going to be typing that G-code in manually to demonstrate that this system works. So now I'm going to be typing in M64 space P1. Now, M64 is a command to turn on the pin, turn on pin 8. And P1 refers to specifically digital output 1. Now, if you use digital output 2, for example, then you would do M64 P2 instead of P1. So, you know, you get the gist here. Now, if we press enter and execute this command, you can see that the light bulb lights up. Now, to turn this light bulb off, what we have to do is type in M65 space P1, and it turns the light bulb off. So back to this plasma cutter. I just want to go straight into this socket. I want to connect directly to the socket because this is where the switch, the button that you press on the torch itself, connects to. So this socket, this plug is called an aviation plug. And this was around, I think, $2, if I remember correctly. And so this saved me from cutting up this cable. So actually it's really convenient because I want to be able to manually use this plasma cutter as well. I want to keep that manual option. I don't want to just fix this plasma cutter directly to the machine and keep it there forever. So yeah, it's as simple as connecting these two pins over to the relay, and from there we can just control it via Linux CNC, and yeah, it'll be just like simulating you pressing the button on the torch itself.
So after the proof of concept was done, I began to put everything onto one plastic container. I did a lot of wiring and tried to make sure everything was neat. I also designed new rollers for the frame and cut them out of some scrap metal manually. It worked out well in the end. Now I went outside and tested the movement, which looked great at first, but I quickly began to notice issues I mentioned before, with the motors being too weak and heating up very quickly. So when I replaced the motors, I had to make my stepper motor drivers much more powerful. Instead of buying better ones, I simply put two of the regular easy drivers in parallel. For some reason, I don't have a good shot of the two boards attached together, but I literally stacked the boards on top of each other and connected all the same pins together in parallel, and that worked. Later, I also added a fan and a heatsink, as you can see. With a lot more current consumption, I had to upgrade my power supply to a 5 amp one, but after that it ran surprisingly well, and here are the first cuts I attempted with the machine. This was my entire setup. I used an old tripod to hold the cables coming from the plasma cutter above the frame. During testing, sometimes I got lucky and it produced reasonable cuts, but most of the time during operation, the pulley system would slip due to friction from the cable system or simply because the plasma torch was lightly scraping against the surface of the sheet metal. Sometimes the metal touching the torch tip was inevitable because during cutting, the sheet metal warps up toward the torch head. You'll also notice the cuts themselves have these weird points where the torch didn't cut all the way through, or some cuts have a wavy appearance to them, and that's because of the erratic movement caused by the suspension of the gantry. This can be clearly seen when the gantry is moving. This could possibly be solved by increasing the tension of the wires, but at that point I would need to switch the pulleys to metal ones to prevent the wires from cutting into them. You'll also notice that whenever I tried to make any cuts, I was always losing steps somewhere due to slippage issues in the pulley system. This can be clearly seen when you look at the letters I tried to cut out, but they were not aligned straight like they should have been. At this point, I was fed up with the old pulleys and I decided that the wire system was simply never going to work, so I bought 20 meters of this fiberglass reinforced GT2 timing belt. I bought new stepper motors, again, because I found a stupid way of breaking the old ones, and here are the motor specifications for the steppers I am currently using in the machine. These are great motors, by the way, and I highly recommend them. And finally, I had to make my own GT2 tooth profile, say that 3 times fast, and create a custom idler pulley around that in Fusion 360, which I then imported into Craftware to slice it into layers, and then 3D printed it out on my 3D printer, which took about an hour and a half. I had to repeat this print 8 times in order to create all the pulleys. I designed the new pulleys to accept the roller skate bearings, and they fit in the machine nicely. I also used some scrap metal to create these clips that held all the tension of the belts. And I also created a rail system for the frame by taking apart some linear bearings I got from a thrown-out drawer, and through careful modification, I was able to make these sliding rails that worked better than expected. So now that you are all caught up on the machine, I think currently it has never worked better. The geared pulleys don't lose steps anymore or slip, and there is no need for those side rollers like on the wire system, and the belts never slip off the pulleys. When I tried to do cuts with this belt system, it exceeded my expectations in strength and in precision. I can cut simple shapes out with ease, and even do more complex designs that require circular motions or arcs, and not have to worry about the belt slipping off. One of the remaining problems is on the z-axis, or the height of the torch tip. That is still fixed at the moment, and depending on what I'm trying to cut out, the heat will make the sheet metal bend and scrape against the torch tip. This time, instead of the machine stopping, it has enough power to move the entire plate of sheet metal when something is in the way. I also tried cutting very thick material, but the limiting factor was not the plasma cutter, it was the 20 amp circuit breaker that I was using, and this cutter goes up to 50 amps. Speed is another important factor that I want to talk about, and I made cuts around 300 to 400 millimeters per minute, but that heavily depends on your settings in Linux CNC.
So when you're in Linux CNC and you go to the Machine tab and go under Calibration, you should see a box like this pop up. Now, Tune 0 is your x-axis, Tune 1 is your y-axis, and Tune 2 is your z-axis. Now, we only really care about the first two tabs. And what I want to bring to your attention is the scale value here. Now, the scale value is important to consider because, for example, in my situation, when I was trying to cut something out in Linux CNC, the object that I put in there was way too big for the sheet metal, and so I had to shrink it basically. Unfortunately, the default of Linux CNC doesn't have any real easy way of manipulating the size of an object that you put in there. So this is what you have to do. My object was too big for the sheet metal, and so I had to shrink it down, and this is how you shrink it down. You change this scale value. So in my case, I changed it from 200 to 150. And what that did is it, of course, shrank the object in Linux CNC, but it also made my gantry slower. It made the speed slower. I didn't change anything to do with the speed. I only changed this number, yet I was experiencing a slower speed. So that's what you have to keep in mind. You might have to compensate for that speed by increasing your max velocity. So instead of hanging around 300 to 400 millimeters per minute, which is a good average value, you would instead may need to double that value to 600 or 700 millimeters per minute in order to see, on average, the same speed that you were getting before. Hopefully that makes sense.
I made this machine to extend my plasma cutter's usefulness because making large signs or parts in a precise way would be difficult if done by hand. But I know some people might not use this frame for a plasma cutter. Maybe you want to make a huge yet cheap drawing robot, or maybe attach a solid-state laser on this thing and etch some big wooden canvas. Maybe you would want to make a huge 3D printer that not necessarily uses plastic but could use paper mache, sand, concrete, or mud as a medium to slowly build up objects. Like I said before, I like the frame design because it's expandable, it's cheap, it's portable, and if done right, it can be precise. I will make sure to provide all relevant links and the download for the Fusion 360 file in case anyone is interested. Now, this machine still needs to be improved, so here's what's next on my list. To further increase performance on this belt system, one major thing that you could do is add tensioner pulleys, and the purpose of those is to simply wrap that belt tighter around the pulley, around the corner pulleys of the frame, and once it's tighter around that pulley, it will have more tension and grip. I also want to replace all the hand-stitched belts with the commercial ones because the commercial ones are much smoother and the hand-stitched ones often cause movement issues. I also need to create a better system of attaching, adjusting, and disconnecting the plasma cutter head, as well as other utensils that I may want to attach to this, like pens and markers if I wanted it to draw. I noticed that the metal clips that I use to tension the timing belts sometimes dig into the rubber and start to cut the belts themselves, and so I need to improve on that as well. The next part will just talk about the software side of designing G-code for this machine. If that doesn't interest you, then you can end the video here. But if you got this far, I hope you learned something, and thank you for watching. So as for designing something in the software, I'm using MakerCam. Now you can use whatever you want. You can use, for example, Fusion 360, and that would be fine too. You just have to understand what type of G-code file you are producing with those programs, and more specifically, what kind of G-code is inside those files. That will be relevant in a minute. You'll see why that's important in a minute, but first let me just design something very simple and guide you through this. Alright, the very first thing we want to do is insert a rectangle. Now in reality, this is going to be a square. We're going to leave all the dimensions the same. So here we have our square, and now we just drag it right by the origin. And there we go. And there we go. We aligned it neatly by the origin, and that should be fine. So we have the square selected. Then we go to Cam, and we go to Follow Path Operation. And now we're going to change the tool diameter to 0. We're going to change the target depth to -0.3. The safety height to the same thing, and the step down to the same thing as well. So basically what we're doing by changing these numbers is changing how much the z-axis goes up and down in the G-code file. And as you know, we do not use a z-axis in our machine, and so most of these options that we're changing do not apply to us. But these are still important options to be changing because this affects how the program goes about making the G-code for the object that we have designed. After we click OK, make sure the box is selected, then go to Cam and go to Calculate All. Now this will create the actual tool paths, and then go to Cam one more time and you can export the G-code. Now make sure to click the follow path operations that you just made and then export your G-code. Okay, so this is how our square looks like in NC Corrector. This is a really useful program to edit G-code, but also to look at how that G-code translates into motion and paths. Anyway, so we're focusing on the z-axis. You notice that there are z-axis commands here down in the G-code, and we're going to be editing those z-axis commands. So here comes the clever bit. Every time the z-axis goes in the positive direction or away from the work, we're going to be replacing that entire command with an M65P1 command. Now, as you know, M65 space P1 turns off the plasma cutter. So every time that the z-axis is going to be going away from the work in the G-code, it's instead going to turn off that plasma cutter, and we're just going to hit replace all because we want to do this for all of the z-axis commands that are in the positive direction. So now we're going to focus on the z-axis in the negative direction, and we select this entire command, and we're going to replace it with our M64 command, because M64 turns on the plasma cutter, and we want to turn on the plasma cutter when the machine is going in the negative direction, which means it's going toward the work. But after that, you can see that our square changed. We no longer have a z-axis, and that's completely fine. Our machine doesn't use a z-axis. Our z-axis for our machine is fixed. And so all we really did is we changed the G-code in such a way to make it workable with our setup in Linux CNC. And yeah, this is ready to be saved and put into Linux CNC so we can execute this G-code. It's really that simple. And I'm sure if you can figure out how to make a script that can edit this G-code like we did here automatically, then this can go way faster and be way easier.